Okay. So to begin with, let me start with our syllabus. The syllabus is weeks 1 to 4. And all topics are important. All topics are equally important. There's no weightage in any sense because if you're asked to find the basis for a vector space, you're not just using the concept of basis, you're also using the concept of a linearly independent set, a spanning set. And then when you're trying to find the basis, you're actually solving some system of linear equations, which is from the previous weeks and all that, right? So all weeks are interrelated and hence all topics are important. Fine?
Yes, ma'am.
Yes, ma'am.
7, 8.8.
Yes, ma'am.
Okay. So we have one more session tomorrow. How do you want this session to go about? Do we discuss week 1 and 2 today, or do you want to focus more on 3, 4?
More on 3 and 4, ma'am.
Okay.
Yes, ma'am. More focus on 3 and 4.
Yes,
So
ma'am.
maybe we'll do
Yes,
one
ma'am.
quick cover of recap of weeks 1 and 2, and then we'll start 3 and 4 tomorrow again. Anyway, Shubhajit will be
Continuation.
taking the session. Yeah,
Yes, ma'am.
yeah. Okay. So yeah, uh, what is a vector? A vector in R2, in R3. What is a vector?
Which satisfies all these 10 axiom.
No, that's a vector space. A vector in R2 is going
Is an
to have two
element, ma'am?
components, right?
Yes, it's an element of the form x comma y.
Yeah, it's basically R cross R, that's all. And then in a vector in
Yes, ma'am.
R3 is going to have three components. So for us, vector, yeah. For us, a vector is not something that has magnitude and direction or anything. Vector is any element of the vector space. So any point x comma y is a vector for us because we know that R2 is a vector space and x comma y belongs to R2. So x comma y is a vector for us. A vector in R2 will have two components. A vector in R3 will have three components. A vector in Rn in general will have n components. So how do we add two vectors? We add them component wise and we do scalar multiplication on the vector component wise. So if I have say x comma y and z comma w, we add them component wise. The first component with the first component, the second component with the second component. And we do scalar multiplication also component wise. Alpha x comma alpha y. And yeah, so these are how we add vectors in Rn. And we are interested only in two operations, addition and scalar multiplication. Scalar multiplication is when you multiply with scalars, real numbers. Then what are matrices?
It is also vector.
Matrices is an array of numbers, right? You just have a set of numbers arranged in rows and columns, right? Yeah. And how do we add matrices?
Component.
Component
Component
wise.
wise.
Component wise.
And the order of the matrix is m cross n if there are n rows and n columns, right? Yeah. And what is the transpose of a matrix?
Rows into columns.
Yeah. So the
Rows column get
transpose,
interchanged.
yeah, the transpose of a matrix will be of order n cross m, and the rows become the columns of this matrix, and the columns become the rows. We add two matrices component wise. We do scalar multiplication on matrices component wise, and then how do we multiply two matrices? Can we always multiply two matrices?
No, ma'am.
Not
Columns
always,
is
but
equal to rows in the
if the columns of first matrix and rows of second matrix are same, then we can multiply them.
Yeah. So if the number of columns of the first matrix is equal to the number of rows of the second matrix, then we can multiply two matrices. And how do we multiply?
Rows into columns. Rows and columns.
First row with the first column, second row with the second column. Can we multiply these two matrices?
Yes, ma'am.
Yeah.
Yes.
Because the number
Yes,
of
ma'am.
columns of the first is equal to the number of rows for this. So you'll do the first row with the first column. So 1 into 2 plus 2 into 4.
2 cross 1.
9.5 and 8.
Huh? What is it? Okay. 3 into 2, 6 plus 4 into 4, 16, something. Whatever that is. 22. Yeah.
22.
We're going to get a 2 cross 1 matrix. We eliminate these two entries. Only if these two are equal, we can multiply, and then whatever is left out will be the order of the matrix, product matrix. Okay. Then what else do we know about matrices?
Various types of matrices.
Okay, yeah, scalar matrices, diagonal
Diagonal
matrices, and all that. Yeah, all those we know. And what determinant of a matrix? What is the determinant of a matrix? How do you find the determinant of a matrix? Can we find determinant of all matrices?
Only square matrices.
Only square
Only square
matrices.
matrices.
Yeah, so the matrix has to be a square matrix first of all. How do we find the determinant of the matrix?
You can go row wise or column wise.
You can do it either along a row or along a
We
column.
can sum up the cofactors with, or we
Yeah.
can take the alternate sign and sum up with the minus.
So how do you find the determinant of a 2 cross 2 matrix?
It's AD minus
AD
BC.
minus BC.
Yeah.
1 into 4
AD
into
minus
1
BC.
into 4 minus 3 into 2. So AD minus BC. So if we have a 3 cross 3 matrix, we will split it till it becomes a 2 cross 2 matrix. Means we know to find the determinant of a 2 cross 2 matrix, so we will do accordingly. Okay. So what is the easiest row along with which we can expand?
First row.
First row or the third column, right? In both cases, there's only one non-zero entry. First row is even simpler because this entry is 1. So we'll do 1 into the determinant of 3, 4, 4, 0. We'll eliminate this row. The row and column where 1 occurs, and then we will do this. What if this was 1? What will the determinant be then?
1 into 0 minus
60.
4.
Minus 1 in
Minus
Minus
1,
1 into. There will be a minus
determinant of 2410.
200 minus 4.
Okay, whatever the answer is. Yeah, this is how you do it. Okay, if we have a 4 cross 4, we will eliminate rows and columns similarly and convert it into 3 cross 3, and then we will do 3 cross 3 by eliminating rows and columns. Okay, or instead, what is minor of matrix? Please mute if you're not talking to me. What is minor of a matrix? Minor of an element?
Eliminating corresponding row and column.
Yeah.
Then
The minor
The
of
matrix obtained by eliminating corresponding row and column.
the determinant of the matrix, right?
Yes, ma'am, the determinant of the matrix.
So given an element, aijth element, the aijth element occurs in the ith row and jth column. So you eliminate the ith row and jth column from the matrix. Whatever is left out, the remaining matrix that you have, the submatrix, you calculate the determinant of that submatrix. That is the minor of aij. What is the minor of 3 here?
0.
0.
So you will eliminate this, and then you will have the determinant of 1, 0, 1, 0. So that is 0. Okay, fine. What is cofactor of an element?
The signed minor.
Yeah.
Minus
So
1
it's
to
just
the power ij.
I plus j
Yes, I
into the
minor
minor
ij.
of
into
aij.
the minor.
Yeah. Okay. And using cofactors is what we find the determinant, right? We get this
Yes,
plus
ma'am.
and minus because of those cofactors. The minus 1 power I plus j that comes from the cofactor. Okay.
Alternate
So,
sign.
Yeah, we'll get alternate sign. Fine. So, what is determinant of A transpose in terms of determinant of A?
Same.
Yeah.
Same.
Well,
Same.
what is determinant of a diagonal matrix?
Multiplication
Product of
the
diagonal
Product of
elements.
diagonal product of diagonal entries.
Not just diagonal matrix, right? Even for upper triangular or lower triangular
Yeah.
matrix, you can just easily calculate the determinant by multiplying the diagonal entries. What is determinant of alpha times A?
Alpha
Alpha
to the power
power
of
Alpha
alpha
to
to
power
the
m.
n into a.
Alpha power n into determinant of A, where n is the order of the matrix A, right?
Order of the matrix.
Yeah.
Yes, ma'am.
If A is an n cross n matrix, you have to take alpha n times outside. So you'll get alpha power n into determinant of A. What is determinant of A plus B?
Determinant
Cannot
of A.
Determinant of a plus determinant of b.
No, it's
No,
not
can't be.
equal to that. Yeah.
Ma'am, could you please repeat what you said about finding the determinant of upper triangular and lower triangular matrix?
It's same. It's the product of diagonal
Okay.
entries. Yeah. This is not equal, right? Take A is equal to 1, 0, 0, 1. B is equal to minus A. Determinant of A plus B is 0, but determinant of A is 1 and determinant of B is also 1. Fine. So this cannot be told. But what we can tell is what is determinant of AB.
determinant of A into determinant of B.
Yeah. Determinant of A into determinant of B. Okay. Then these are what we know about determinants. Okay. What is system of linear equations?
Ax
Yes,
is
is
equal to
equal to
Yeah.
b.
So given
when we can present it in.
system of
Yeah.
linear equations means you have a set of linear equations that you want to solve simultaneously, right? You want to find one common solution satisfying all the equations. So that can be represented in the matrix form as Ax is equal to B. What will be the entries of the matrix A?
Coefficient.
Coefficient matrix.
Yeah. And what will X be?
Variable.
Variables.
Yeah. So if I have say two equations in two variables, my coefficient matrix is going to be 1, 1, 1 minus 1, x, y, and the B vector is 1, 0, right? So this is a representation of this system in the matrix form. Ax is equal to B. Now, when I'm looking for a solution for this system, I'm actually trying to find out an x that satisfies this equation, right? I'm looking for x. A is given, B is given. I'm looking for an x. So when I'm trying to find a solution, I'm looking at what are the values of x that satisfy this system of linear equations. So a system of linear equations can have three possible solutions. One is a unique solution, in which case there is one x satisfying the Ax is equal to B. Another is when there are infinitely many solutions. This happens when there are infinitely many vectors x satisfying the equation. And then there is a no solution case, the case where no x satisfies Ax is equal to B. There is no possibility of exactly two solutions or exactly three solutions. It's just one of these. So if how do I decide the order of the matrix A, the coefficient matrix A? Can you tell me what the number of rows represents?
Number of equations.
Number of equations.
Number of equations.
Number of equations.
And n better.
And n represents the number of
variables.
Variables.
So if I have an m cross n matrix, it means that I have an m cross n system. That is m equations and n unknowns. So if I have a square system, n equations in n variables, then how do I check whether it has a unique solution or not easily? I have an n cross n system.
Finding the determinant.
We need to find the determinant.
When the determinant is not equal to 0, I know that there is a unique solution. When the determinant is equal to 0, it can be either of the other two cases. It can either have infinitely many solutions or it can have no solution. So that we cannot conclude. So this just eliminates one of the three. It just eliminates unique solution case. But when determinant is not equal to 0, we always know that there is a unique solution. Can you tell me what that solution will be?
Trivial 0.
No, why will it be?
Ma'am,
A inverse B.
we can use Kramer's rule to find.
Okay.
Zx is equal to A inverse B.
A inverse B, right. So if I put x is equal to A inverse B, what do I get? A into A inverse is identity, right?
B.
Yeah, B.
Yeah, X is equal to B then.
I get B, right?
B. Yes,
So
ma'am.
in the place of X, I put A inverse B, and I get that it is satisfying this, which means that is a solution, right?
Yes, ma'am.
Yeah, and because the inverse of a matrix is unique, this is the only answer possible. A inverse B is the only answer possible. So when you have a square system, it's easy that you can just take the determinant, check the determinant. If the determinant is non-zero, you know that there is a unique solution. We didn't discuss inverse. What is inverse of a matrix?
1 upon determinant of A into adjoint.
1 by determinant of A
Adjoint
into
A.
adjoint of A.
Yeah, and the inverse exists only when determinant of A is not equal to 0. So when
Nonsense.
determinant of A is not equal to 0,
Invertible.
you call such a matrix as invertible matrix. What is adjoint of A?
Matrix of cofactors.
Cofactor matrix.
Transpose of the
Transpose.
Transpose of cofactor.
Transpose of
Yeah. Cofactor. Yeah. And what is a cofactor matrix?
Every
Have
entry
to call the element.
replace
Cofactors
cofactor.
of corresponding element.
Yes. Every entry of the
Cofactor
cofactor
matrix of
matrix
all matrix.
is the cofactor of the corresponding entry of the matrix. That is the cofactor matrix. Okay. Okay. So then what else? How do you find a solution? How do you solve for the solutions?
Excuse me, ma'am. Sorry to interrupt.
By Gaussian elimination.
Yeah, we can do that. Yeah, someone has a doubt. Yeah, please, sir, go ahead.
Actually, is this session you are taking it as a revision, or people are allowed to ask doubts as
You
well?
can ask doubts. You can stop me at any point of time.
Okay. For regarding questions.
You can
Because
ask.
if you are going for revision, then I will ask it in the end. That's why I asked it.
Maybe we'll do one thing. I'll discuss the topics and then take doubts related to that topic. Is that okay?
Okay.
Yes, ma'am. Ma'am, can you discuss elaborate for rectangular matrix also here?
Yeah, we'll do some
Solution of
problems.
system.
Yeah.
Ma'am, for this, can you explain with rectangular, like the solution part?
Yeah, we'll do that. We'll do that. Okay.
Even one example for inverse of the matrix.
Okay. Okay, fine. So did I miss out something important here? System of linear equations, solving. That's the next thing. Okay, fine. So let's find the inverse of a matrix. Let's take, say, we'll keep it simple.
Sorry for interrupting, ma'am. Hello.
Yeah.
Ma'am, you are recording this session, so after the session, you will upload on YouTube or?
Yeah, it'll be there on YouTube.
Yeah, because someone keep asking in the chat that YouTube link is not working. That's why.
Oh, okay. Yeah. There was some problem streaming because it said someone is there in the meeting because of which YouTube's recording cannot happen. Means the stream.
Yeah, ma'am, that's why I asked. Hope your doubts get clear. Thank you, ma'am.
Okay. Okay, if your mic is not working, you just put it on chat. Someone can tell me if if there is any important doubt, someone can unmute and tell me. I'll clarify that. Okay. So how will we find the inverse of the matrix? Inverse is 1 by determinant of A into adjoint of A. Do you know any other way of finding the inverse?
Yes, ma'am.
There is one way which was told in the tutorial by Shubhajit sir.
The Gauss-Jordan method, right? Using Gaussian element.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
So we will
I think
do
using Kramer's rule as well. We can.
no, using Kramer's rule, you don't find inverse. You find the solution to a system, right? You solve AX is equal to B using Kramer's rule.
I saw somewhere that using this idea means we are solving basically equations, but using this idea of Kramer's rule, we can also find out the inverse.
Oh, yeah. Okay. You put X is equal to 1, 0, 0. Not X. What do you want to find out? You want to find out A inverse. B is equal to 1, 0, 0, 0, 1, 0, and 0, 0, 1, and solve 3 systems, right?
Yes, ma'am. It was similar to this only.
Yeah. You can do that also. Okay, but let's not get into all those details. Yeah, that's not needed. So yeah, we will find the inverse by finding out the adjoint of the matrix and the determinant of the matrix. So what is the determinant of this matrix?
1.
Yeah. You can expand it along the first row. So that's going to be 1 into determinant of 6, 5, 1, 1. So this is 6 minus 5, 1. So the determinant of this matrix is 1. Okay. What is the minor of A11?
1.
Yeah, you will eliminate that row and that column. So 6 minus 5, 1. A12?
0.
0.
Why is it 0?
It's 9, ma'am.
9.
9.
4 plus 5, 9. A13?
10.
10.
10.
10. Okay, so whoever said the minor of A12 is 0, is it clear why it is not 0?
Yes, ma'am.
Yeah, you shouldn't multiply the element. You should just eliminate the row and column where it.
Ma'am, you are not audible.
Ma'am, you are not audible.
Ma'am is not speaking right now.
Am I audible?
Yes, ma'am.
Now what?
Yes, ma'am.
Yes,
Yes.
ma'am.
Okay. Yeah, what is the minor of A21?
0.
0.
Yeah, the determinant of this matrix 0, 0, 1. So it's 0. What is the minor of A22?
1.
1.
1 into 1,
One.
minus 0. 1.
Minus.
A23?
1.
1 into
One.
1. Right.
Minus 1.
No, the minor won't have a minus sign. Minor will have only positive sign.
Hello.
Cofactor will have the negative sign. A31?
Okay.
0.
0. 0.
A32?
5.
5.
5 minus 0. 5. A33?
6.
6.
6.
6. Right. So these are the minors. So the cofactors will be
1. Minus
1
9
minus
is 10.
9.
Minus 1 to the
you
power
do
I.
minus 1 power I plus 2. So for A21 it will 1 2 it will be
Minus 9.
Minus 1 raised to 1 plus 3.
1.
yeah 1 plus 2. So when you add the indices, if you get an odd number, you will put a minus sign. If you get an even number, you will keep it positive. Means the same sign. A13 will be 10.
10.
10.
10.
A21 will be minus
0.
0, that is 0. A22
0.
is 1.
1.
1.
A23 is
Minus
1.
1.
Minus 1.
so now it is minus 1. A31 is
0.
A32
0.
Minus 5.
Minus 4.
minus 5.
Min-
A33
6.
yeah.
6.
So the cofactor matrix is 1 minus
Transpose.
minus 9 10 0 1 minus 1 0 minus 5 6. Here I have written it column wise. I should have written it row wise. Okay, but I wrote it column wise. A1 2. So this will come here. So this is the cofactor matrix. What is the adjoint?
Transpose.
It's a transpose.
Yeah. 1 minus 9,
Transpose
10.
of
1 minus 9,
minus 1, 0, minus 5, 6.
6.
So what is the inverse of the matrix?
1 by determinant of a
1 by determinant of A.
Divide by determinant.
Yeah, we already found the determinant to be 1, right?
1.
So it's nothing but the adjoint of the matrix.
See.
What will be the determinant of my A inverse?
Which we say
1 by
1.
1 by
1.
determinant. 1 by determinant of A.
1.
We already know the determinant of A, so it's 1.
Ma'am?
Yeah.
Ma'am, we in minors, we didn't take determinants, right? We just eliminated that row and column and just remaining thing we had is multiplying.
No. We are finding the determinant of the remaining submatrix.
Okay. Thank
That's
you.
how you get 6 into 1 minus 1 into 5.
Okay. I was confused with things.
Now is it clear?
Yes.
Ma'am, we can also use row transformation method to calculate the inverse, right?
Yeah, we can. We'll do that also. For the same matrix, we'll do that
Yeah.
also.
A into A inverse equal to B, where B is identity matrix, and we
Yeah.
could solve for that.
Yeah, we know A into A inverse is equal to identity. Using this, we can use the row transformations and find the inverse of the matrix. So we'll do that. Before getting there, what are the elementary row operations?
Excuse me, ma'am.
Yeah.
Here the adjoint matrix, I think it's the original cofactor matrix. It's not the transpose of cofactor matrix.
This is the cofactor matrix.
Yes, ma'am. No, ma'am. The cofactor matrix was the first row of cofactor matrix was 1 0 0.
No. I have written it. I should have written it the other way. I wrote A12 here.
Okay.
A13 here. Yeah.
Okay, got it.
Yeah.
Ma'am,
So
someone asked
A12
the
is-
question in the chat that can minors be negative? So yes, minus can be negative, right?
Yeah. Oh, here we got all positive.
Yeah, that's why maybe the question has come.
Yeah, minus can be negative.
Right.
If the minor here was minus 5, what would the cofactor be?
It would be
Plus 5.
Mi-
Plus 5.
Yeah.
plus 5.
Minus 1 power 3
Power
plus
3
2
plus
into
2.
minus 1.
Yeah, right.
Minus can be negative, no issue. It can be any number.
Yeah, thank you, ma'am.
Okay, so what are the elementary row operations?
Type 1 interchanging rows.
We can interchange row, multiply a row by a scalar, and then multiply a row to another row. We can add a row to another row with multiplying a scalar. Yeah, the same.
So you can interchange two rows. You can multiply a row with a scalar, and you can do this operation. You can replace a row with the sum of the row and scalar times another row. What is the effect these elementary row operations have on the determinant?
First term, no effect. Second,
No change. Second one?
sign changes.
Sign gets changed.
Yeah. You multiply by minus 1.
And
third one?
Multiplied by that.
Alpha times determinant of.
Determinant.
Yeah. So whatever is the
matrix.
scalar you are multiplying with, that will be the determinant will get multiplied by that. So that is why we had done something, no, determinant of alpha A. If I take determinant of alpha A, I am multiplying alpha with every entry of the matrix, right? So I am replacing every row of the matrix with alpha times that row. So that is why we get alpha power n into
Alpha to the
determinant
power
of
n. Determinant of A.
Okay. So using the elementary row operations, we can solve a system of linear equations by converting it into a row echelon form, right? What is row echelon form?
Below 1, all should be 0.
One triangular is matrix.
Convert the matrix into upper triangular.
Yeah, you're somewhat converting a matrix into an upper triangular form. Not exactly upper triangular, even rectangular matrices can be converted. So in some sense, we are converting it into an upper triangular form. So say, let's take an example, or let me just write down what is row echelon form. So below, the pivots in each row should be 1, right?
No, ma'am.
Yes, ma'am.
What is pivot?
Yes, ma'am.
Leading
It,
entry.
Leading entry.
Leading non-zero entry. Is
if the
this
row
matrix
is non-zero, then
is this matrix in
zero.
row echelon form?
Yes, ma'am.
Yes,
Yes,
ma'am.
Yeah.
Yes.
ma'am.
This is not the leading
No,
entry,
no,
no?
no.
Means this is the leading entry. This is not 1. The leading non-zero entry should be 1. Pivot means the leading non-zero entry of a
No,
matrix.
but we can swap it
Ma'am,
easily and it would again become.
and that is only echelon form in which the below rows are not 1 and of the same form.
Is this in row echelon form or not?
Yes, ma'am.
Yes, it is.
Why
Oh,
not?
Yes, ma'am, it is.
Corner vectors are
Zero rows are below
Yes.
non-zero rows. Fine. Pivots should be 1. The first non-zero entry in each
Yes.
row should be 1. What is the first non-zero entry in
Can
the
you show
first
this
row?
for the 3x3 matrix?
One.
Yeah. We'll do an example.
1.
1. So that's a pivot. The pivot is 1. What is the non-zero entry of the first non-zero entry of the second row?
No
Uh,
entry.
there is
We don't have.
Non-zero entry. Yeah. So we are not bothered about what leading entries are or anything. Then what
Ma'am.
pivots?
Will transpose of REF be also REF?
No, the transpose of this matrix is this. No, is this an REF?
No, ma'am.
No, right? Zero rows are not below non-zero rows, right?
But we can simply, perform that column operation. I mean, just transpositions. 1, 0, 0. And
Are
shifting
you
that
telling you can interchange the rows?
Swap.
Yes, ma'am.
That will have minus sign.
No. See, you can convert any matrix into row echelon form. Wow. Whatever be the matrix, you can convert it into row echelon form. The question was, is the transpose of REF in REF? It's not, right? But you can convert it into REF. No trouble with that. Any matrix can be converted
Conversion
into.
and the actual presence are different things in REF.
Yeah. This matrix is not in row echelon form, but you can convert it into row echelon form.
So, ma'am, the basic rule for pivots are that there should be a zero row below the non-zero row.
No. Is this matrix an REF?
No.
Yes, ma'am.
yes, ma'am.
Yes, ma'am.
Why not? If there is a zero row, it should be at the bottom. It shouldn't come on top.
Okay.
Yeah. This is a pivot. This is a pivot. Entries below the pivot should be 0, right?
Yes, ma'am.
Yeah.
Excuse me, ma'am.
Yes.
If all the entries are zeros, will it be treated as in REF, ma'am?
Yeah. There
Yes.
are no non-zero entries at all, no? For the pivots to be 1. So this condition is vacuously satisfied. All 0 rows are below. They are all 0 rows only. Entries below the pivot should be 0. There are no pivots at all. So we needn't be bothered about this condition, right?
Right. Thank you, ma'am.
How in the second matrix what you have drawn, there are 0 rows below?
No, if there is a 0 row, it should be below. There are no zeros, that's all.
Okay.
It doesn't say that there should be 0 rows. If there are any 0 rows, they should be below the non-zero rows.
So for the second pivot which is there 1, for that the condition doesn't satisfy then.
Why?
The 0 rows are not below.
No. How many rows does this matrix have?
2 rows.
Is there any row which has completely 0 elements?
No.
Then why are you even bothered about this condition?
Ma'am, it is like this, no, ma'am. Like
So it is not a
it is
compulsory
not necessary.
optional
It is not
condition.
necessary. Okay.
See, the question someone asked, no, is this an REF?
Yes.
Yes, ma'am. It is.
So why are you not telling that pivots are not 1?
Okay, so either of the condition should be satisfied. It's not like all of the
No,
conditions.
all the conditions should be satisfied.
If they are present.
If they are present. See, there is no pivot at all here, right? Pivot is
Right.
leading non-zero entry. There is no non-zero entry at all, let alone a leading non-zero entry, right?
Okay.
So none of the entries are 1. So this is satisfied. There are no pivots at all. So this condition is vacuously satisfied. Only if there are pivots, it should be 1, right? There are no pivots at all. So it is satisfied, right?
Got it. Thank you.
Madam, what is vacuously satisfied means?
Vacuously satisfied means that cannot even happen.
Ma'am,
So we
in
assume it is
matrix
true.
1,
Means it is satisfied.
ma'am, in matrix 1,
Okay.
is that one a pivot point?
Yes.
Yeah, because that is the first non-zero entry of the first
Okay,
row.
okay.
Yeah. So, and any matrix can be converted into row echelon form. Okay, let's convert this matrix into row echelon form. Is this in row echelon form?
No, ma'am.
No.
No, ma'am.
Why is it?
No,
Because
ma'am.
below 1 there are non-zero entries.
So you look at what is the pivot of the first row. The first non-zero entry of the first row is 1. That is a pivot. So below it, all the entries have to be 0. How can I
Zeros.
convert this entry and this entry to become 0?
By
R2 minus 4
R2 minus
R2 minus
R2
Yeah.
R2
You will
minus 4
perform
R2 minus
elementary
2
row
R1.
operations, right? R2 minus
R3 minus 2 R1.
R1. R3 is R3 minus 2R. So you will perform elementary row operations and convert a matrix into row echelon form. So the first row remains as it is because there is no operation performed on it. The second row is replaced with the second row minus 4 times the first row. So that's going to be minus 1,
0, 1, 6.
Minus 12 is minus 6.
Minus
Right?
6.
Minus.
And then 0, 0, 0, right?
0.
Is this in row echelon form?
No.
no, ma'am.
Why not?
Because
Because second
the
second row
leading
is
entry is
Second
not
row is
1.
minus 1.
Minus.
Yeah.
It should.
So the first row is
Second
over.
row.
We identified the first pivot and made sure that below the pivot there are no problems. So we made them all 0. Next, we go to the next row. Now the first non-zero entry of the second row is minus 1, whereas our pivots were supposed to be 1s. So for that we will multiply
R2 by
R2
minus 1. Yeah.
Ma'am, instead, why not we do like this? 4R1 minus R2.
No, your elementary row operations are these. You cannot do alpha. What did you say?
4R1, that means R2 is equal to 4R1.
Alpha Rj plus Ri.
Yeah, ma'am, R2 minus 4R1 you written, no, ma'am. Instead that 4R1 minus R2.
Both are the same, no? It doesn't matter which one you write first, right?
That will change the second row.
Yeah,
Zero
that will change
change.
the second one. No?
No, no,
So zero will be
R2
not
is
there.
what? You're saying?
4R1 minus R2.
4R1 minus R2.
Oh, no. See, you're not allowed to do this. You have to keep R2 as it is. You shouldn't do any scalar multiplication on R2.
Okay.
Means
So it will always
basically
be
you will
R2
doing
minus
this in
4R1.
2 steps. You
Ma'am,
will
I
be doing
think-
this in 2
Yes.
steps, right? First you will do R2 minus 4R1 and then you will multiply it with a minus sign, right?
Okay. So we are not allowed to do in this step like this.
Yeah, basically you're not allowed to do this because it will affect the determinant. Otherwise, no problem. Yeah.
Okay.
And determinant will be anyway affected.
Yeah, it will be affected. Agreed. No, but the elementary row operation
It
doesn't
can be done,
allow
but
this.
that will change the zero.
See,
Zero
when you
bar.
do that operation, you are combining 2 elementary row operations.
Yes.
Ma'am, what will we do if the first element of first row is anything else rather than 1?
We will make them 1.
Divided.
Yeah.
How? Like by dividing?
How did you make this
by
entry?
scalar.
Like by dividing, no, ma'am. So like we are multiplying with some scalar in that case.
You're dividing
Yes,
by
that
minus
is
1
allowed.
also, I can tell, right?
So so we can write it in that way. 4R1 minus R2, I guess.
What?
If we divide the first row by something, that is also means we are multiplying with some scalar, right?
Yes.
Yeah. No, see, in that case, you will be combining two elementary row operations. You cannot define elementary row operations. They are already defined. And when you're converting it into REF, you are allowed to do only elementary row operations.
Okay.
So if
Ma'am,
you
also
combine
with
these two elementary row operations, you can write it as what? Alpha times Ri plus alpha Rj, right?
Okay.
But you're not allowed to do that. You're combining two elementary row operations. You should perform one elementary row operation. In the sense, okay, not one elementary row operation. Don't simultaneously do two things on the same row.
Okay, but
When
we
you do
can
4R1 minus R2, you're
in 2 steps
simultaneously
we
doing
can do
two
that,
things,
right?
right? One is you're doing a scalar multiplication on R2 and you're adding it with another row, right?
Okay, like we can do it in 2 steps, right?
Yeah.
Okay.
You have to do one step. Means one row which is already getting affected cannot involve in any other operation in the same step. So now is this in REF?
yes,
Yes, ma'am.
Even if we
yes,
didn't
ma'am.
have a
Yes.
zero row, if we ended up like this, even then it was an REF. But then, yeah, got
Now,
a zero row.
Ma'am, the matrix just previous matrix where there is -1. That matrix is something called echelon form.
No, it will be in echelon form if the pivot is 1, but the pivot is -1 here, no? All the
This
pivots
is
have to be 1.
yeah, I understand. But this form of matrix is called nothing, or it is not subset of any.
This is nothing.
I
This is
think
row
from here
echelon
we
form.
can see that rank is 2.
Yeah.
We used to calculate. We used to evaluate like that one.
Yeah. You can check the rank from here also, but this is not in REF. This is only in REF.
Okay.
You will get the rank here because you just have to do one scalar multiplication to convert this entry into 1, right? That's not
Yes.
going to change the 0 entries or non-zero entries.
There also we used to call that it is in echelon form kind of thing.
No. It is in echelon form only if the pivots are 1.
Okay.
Is this in RREF, reduced row echelon form?
No, ma'am, it's not.
Why not?
Yes.
No, ma'am.
Because
Because
of
the second
that
column
two.
containing pivot
Second
has
column
non-zero
2 is there.
entries.
It should be 0.
Yeah. Here we want elements above pivots also to be 0, right?
Yes, ma'am.
Not just below, above pivots also should be 0. There is a pivot in the first column. There is no entry above it, so no problem. There's a pivot in the second column. There is an entry above it, which is not equal to 0. So you have to convert it into 0. How will we do that?
R1 minus 2 times of R2.
R1 minus 2R2. So we'll get 1 minus 0, 2 minus 2, 3 minus 12. So that's minus 9, 0, 1, 6, 0, 0, 0. Is this in row echelon form?
Yes,
Yes.
ma'am.
Is this in reduced row echelon
Yes,
form?
ma'am.
Yes.
No,
Yes,
ma'am.
ma'am.
Yes, ma'am.
No.
Yes, ma'am.
Why not?
Yes.
Why is it
Yes,
not
ma'am,
in
it is.
reduced row echelon form?
It
There are
is.
2 pivots
It is, ma'am.
and the columns containing pivots don't have any other non-zero entry. Then why is it not in RREF?
It is in RREF.
It is in RREF.
The person who said it's not in RREF, can you tell me why is it not in RREF? Is it clear that it is in RREF?
Yes.
Okay, fine. So you can convert any matrix into a row echelon form or a reduced row echelon form, and using this we can solve a system of linear equations. So if we want to solve Ax is equal to b, what we will first do?
We need to form a
Yeah.
matrix.
You will write down the augmented matrix, which is nothing but the matrix A, and the last column you add one more column, which is the B vector, and then
Ma'am, can you scroll up just a minute? Ma'am, there, like when we are reducing to RRF, we are doing the operation like R1 minus 2R1. Then here we are using two operation like we are multiplying and
No,
simultaneously we are
R1
doing.
minus 2, R2, not R1.
Okay.
So here we are not doing something on R1, we are doing something on R2.
Yeah, you're replacing R1 with R1 plus some scalar multiple of some other row. You're not doing anything
R1
to
is
R1.
at ease. Yeah, R1 is at ease.
Okay, ma'am. Thank you. You can proceed.
Okay, so you will write down the augmented matrix when you want to solve a system of linear equations, and then
Excuse me.
Then we can convert A to reduced row echelon form or row echelon form by applying some elementary row transformation.
yeah, so you'll apply elementary row operations on the augmented matrix and convert it into REF or RREF, and then solve this system. Whatever is the solution to this system is, that is the solution to the original system. The advantage of solving this system is that it will either be an upper triangular system where you can do back substitution and find the values of the variables, or it will be a diagonal system where you will get the values of the variables directly. Right?
Yes, ma'am.
Yes, ma'am.
Someone had a doubt, right? Someone
Yeah.
stop. Yeah.
So is this same as Gauss elimination or is it something else?
Yeah, this is only Gaussian elimination. Doing this is Gaussian elimination.
Okay.
So suppose I have a system. I don't know if it will have a solution, but let me just write down something. So if I have something like this, what will be the matrix form of this system?
1 1 1
1 1 1
1
0
1 minus 1
0 1 minus 1
1 2 0
1 2 0
x
So
minus
x, y, z equal to
102 102.
equal to 0 2.
I want to solve this system of linear equations. So if I want to solve it traditionally, I will multiply one equation by something and all. We'll do substitution and all that. Okay, fine. But we'll do Gaussian elimination. So what is the first step in Gaussian elimination?
Augmented
the augmented matrix.
1 1 1 0 1 minus 1 1 2 0, and then you will add the last right hand vector as the last column of the augmented matrix, and now convert this into REF. Yeah.
REF.
So this is my pivot. Fine. This is already 0, nothing to do. I want to make this entry 0. So R3 will be replaced with
R3 minus R1.
R3 minus R1.
Yeah. We will make sure that we are doing all the operations on the right hand vector also. That is why we are doing the augmented matrix, doing it on the augmented matrix. 0 minus 1, 2 minus 1 is 1. Okay. Does the system have a solution? Can you tell from this step?
No solution.
Yeah. Why?
Because the third row, second and third row has a different.
Second row equation says y minus z is 0. Third row says y minus z is equal to 1. This is not possible. So it does not have a solution. But still, this is not in REF. We have to go one more step further. Pivot, no problem.
But as soon as we found that they don't have solution, are we required to continue it further?
No. It means you are
can dare
to find
stop
solution, right? So you have done that. You have told that there is no solution.
But to find a rank.
But then the procedure stops when you find the REF.
In case of finding the rank, we will have to do things.
But then rank has nothing to do with solving the system, right? If you're looking for solution, then this is well enough. 1 minus 0 is 1. Yeah.
Yes.
So this system does not have a solution because the last row of the matrix, coefficient matrix, is all 0. But corresponding to that row, we have a non-zero entry. So no solution. So whenever we have a 0 row, if we want the system to have a solution, the corresponding entry on the right hand vector should also be 0. Right?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah. So let's assume this was 0. How will we solve?
Ma'am, can you please repeat what you said at last, ma'am?
So now I have this, right? Last row is 0 and the right hand vector is 1, right?
Yes, ma'am.
So this system is nothing but x plus y plus z is equal to 1, y minus z is equal to 0, 0x plus 0y plus 0z is equal to 1. Is this equation possible?
No, it's not possible.
Yeah. So whenever you have a 0 row, the corresponding entry of the right hand vector should also be 0. Only then we will have a solution, right?
Okay, to have unique solution.
Not unique solution.
Infinitely many solutions.
Okay, infinitely. Okay.
No.
Okay. So suppose this was 0. My system will be this, right?
Then infinitely many solutions. No?
Yeah. Now it's easy to solve. You have a triangular system. So you'll get x plus 2y is equal to 1. So x is equal to 1 minus 2y. So how many solutions does this system have?
Infinitely many solutions.
Infinitely many solutions.
We'll have infinitely many solutions because one of the variables is
Independent.
free to be chosen. Yeah. So the concept of independent and dependent variables, we consider that only in RREF. So in RREF, columns containing pivot. Columns correspond to variables, right?
Yes, ma'am.
Yeah. You take columns containing pivots and the corresponding variables are called
Dependent variable.
Yeah. Whenever you have a
No, it
pivot,
means
the
if there is no
corresponding
pivot
variable is
in the
dependent.
column, then there will be infinite solution.
Yeah. When you have independent variables, there will be infinitely many solutions. Columns not containing pivots correspond to independent variables. Here is a column without any pivot. So Z is independent, right?
Yes,
You're
ma'am.
free to choose Z. Once you choose Z, Y is fixed. And once Y is fixed, X is fixed.
A column without pivot is independent or dependent?
Column
Independent.
without pivot is
Independent.
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 Okay.
So I had a doubt.
Can you show an example of dependent and independent?
This example only we can take, right? So is this matrix in REF?
Yes.
Yes, ma'am.
Yes,
It
ma'am.
is.
Is it in RREF?
No, ma'am.
No, ma'am.
No, ma'am.
Why?
Because the 1/2th entry is 1.
Yeah.
We need to convert it to
The
0.
pivot and above the pivot we have a 1.
Equals to not 0.
So we will do R1 is R1 minus R2. 1, 0, 2, 1, 0, 1, minus 1, 0, 0, 0, 0, 1. Is this in RREF?
No, ma'am.
Yes, ma'am.
Yes, ma'am.
So there is a pivot here.
Yes, ma'am. It is.
There is a pivot here. So column variable corresponding to the first and second column, X and Y, are dependent and there is no pivot here. So Z is independent.
X3 independent.
Z is independent. Yeah.
Yeah.
Ma'am, so
Ma'am, now can we say that X2 is dependent on X3?
X2, Z, Y is
Both
dependent
X1
on
and
Z.
X2 is dependent
Yes.
on X3.
Ma'am, but here, as previously you said that if there is independent column, if there is any column where there is no pivot, then we can say that system are having infinite solution. But here it is not infinite solution.
No. If whenever you have a 0 row, the corresponding entry has to be 0 in the right hand vector. Only then there will be a solution. If there is a solution, there will be infinitely many solutions. If there are independent variables.
Ma'am, when we are finding dependent or independent variable, then we have to convert a matrix to RREF.
Yeah, the concept of dependent and independent variables is in RREF only, not in REF. But if you look, it will be the same even in REF.
Okay, ma'am. And when we are finding the solution only, then we can convert the matrix to REF.
REF is enough. But if you do RREF, you will get the solution directly. Like, see, from the second, so when you convert it into REF, after you find out Y here, you will go back and substitute to get the value of X, right?
Yes.
But when it is an RREF, you needn't go back and substitute, right? This entry is 0. So the value of y is not needed in the first equation, right?
Yes.
Yeah, you get the answer directly here. That's why RREF is better. But to convert to RREF, you have to do some job.
Ma'am, I had confusion with this concept. See,
Which
in
one?
in this reduced row echelon form which you have just written, right? If the last value is 001.
Here, this one, is it?
Yeah. So, yeah, instead of that 000, if it is 001.
Oh, here, okay.
Yeah. This is now not in reduced row echelon form, right?
Yeah,
Okay.
it is in row echelon form, but it is not in reduced row echelon
Okay.
form. Right.
So let's assume this comes in reduced row echelon form. Then our value is x3 equal to 1, right?
Yeah.
In that case, is x3 dependent or x3 independent?
You have a pivot, no? So it is dependent. Are you allowed to choose any value for x3?
No.
No, the only value that you have
we
is
are
1.
not.
Fixed.
Yeah. It's fixed.
Okay, so it is independent.
Ma'am, suppose if it is not pivot element.
Yeah, there was some confusion in what.
If it is independent, you
then,
have the freedom to choose any value for that variable.
so can we say that then x1 and x2 both are dependent on x3?
Ma'am, we can say that
I'm
here that
assuming that the third element is not a pivot element.
Ma'am, here we can say that x1, x2, x3 are dependent variable, but v1, v2, v3, the three vectors are linearly independent. Sorry.
Yeah, if you have all dependent variables, how many solutions will the system have?
Ma'am, only one
All
solution.
dependent.
One
Unique
solution.
One unique.
Dependent means we get the value straight away. So all the values of all the variables can be got straight away means it has only one solution. If there is an independent variable, then the other two cases arise. If whenever you have a 0 row, the corresponding entry is also 0, then there is a solution. And if there is a solution, there will be infinitely many solutions if we have an independent variable. Independent variables means we are allowed to choose any value for it. So we can choose any value. Each one chooses a different value, we are going to get infinitely many solutions.
But here that 0 should be instead of 1, like corresponding the last, it should be 0. Then we can have.
Then it will be infinitely many solutions. In this case, no solution.
Ma'am, can you please scroll up? Okay. Hello, ma'am. Actually, when it is asked that is there any infinite solution, and second option is there no solution, and to solve such kind of question, we have to form this augmented matrix, right? And then after means converting to row reduced row echelon form, and then we can answer the such type of question.
Yeah.
Okay.
Once you reach this stage, you can answer.
Okay. Thank you.
One question. Small.
Excuse me.
If the last entry of 1 in the augmentation part, if that is 0, then this system has unique solution.
Will the system have a solution first of all?
No solution if there is 0, 0, 0.
No, why?
No, ma'am. It will have solution. Infinitely many solutions.
It will have solution, ma'am. Infinity many solutions.
There is no pivot here, which means z is independent. You can choose any value for z. The last equation is 0x plus 0y plus 0z is equal to 0. That we know. That's nothing new. This is something that's known. That information. There is no information from the third equation.
But if there is 1 in the last row, then there
Then
will be
there
no
is no
solution.
solution
No
because
solution.
for the same reason. I know the left hand side is 0. 0x plus 0y plus 0z is 0. But I'm telling it is equal to 1. That's not possible, right? 0 cannot be equal to 1.
Yes, ma'am.
Is it okay to discuss an activity problem, ma'am?
Yeah, sure. Or should we just tell what Kramer's rule is and then I think we'll be done with 1 and 2.
Sure.
What is the Kramer's rule? When can you apply the Kramer's rule?
When the matrix A is a square matrix.
Invertible. Yeah. How will you find out xi?
By replacing
By putting ith column to B.
Yeah. So in the matrix A, you will replace the ith column with B and then find the determinant of that matrix and then you'll divide it by the determinant of the original matrix. So you're going to get the exact values for x1, x2, xn, right?
Yes, ma'am.
So it's a unique solution.
Can
That
you
is
do one example and through this and make us clear these definitions of Kramer's rule?
Yeah.
Kramer's rule.
So this system does not have a solution. We had an invertible matrix, right? This one. 1 0 0 4 6 5 1 minus 1 1.
And madam, in Kramer's rule, if determinant is 0, then
You cannot even apply the Kramer's rule.
no, then we cannot say that it has no solution or infinitely many solutions.
No.
Why?
No, for applying the Kramer's rule, you want determinant to be non-zero because you're dividing by it.
Yes.
Minus 1, 1, 1. Okay. So now we know the determinant of this matrix is 1. Let's try to solve this system. How many solutions will this system have?
Unique solution.
Yeah. Whatever be the value of B, x is equal to A inverse B is always a solution, right? We already found out A inverse.
Yes.
Did someone keep note of that? 1 0 0 minus 9 1 minus 5 10 minus 1 6.
Ajit, please mute. Ma'am, it means whenever there is a inverse of a matrix possible, then there is a unique solution.
Yeah. That's not the only case, but if the matrix is invertible, then there is a unique solution. Minus 9, 1 minus 5, 10 minus 1, 6.
-1 6.
Yeah. So what is this? 1.
Ma'am, x, y, z should be written. 1, 2, 3, 9 written.
No, I'm finding out B, x, A inverse B.
Okay.
X, Y, Z.
I'm trying to find out x, y, z. Like this. A inverse B. So minus 9 plus 2 minus 15. Whatever that value is. 24 plus 2, 22. Minus 22.
Minus 22.
And then 10 minus 2. 8 plus 18. 26. So I know the solution. This is one way of finding the solution. We'll do Kramer's rule as well. So by Kramer's rule, what is x1? We know the determinant is 1. We already calculated. What is x1 or what is x here?
First of B.
1 by determinant of A. Okay, determinant of A xi by determinant of A. I can ignore determinant of A because it is 1. Okay?
Yes,
ma'am.
So determinant of A xi. You will replace the first column with the right hand vector. 1, 2, 3. 0, 6, 1.
0, 5,
0, 5, 1. And then you will divide this answer by determinant of A. which is equal to 1. So just find this determinant. I can expand along the first row. It's going to be 1, right?
1.
Yes.
Yes.
Yeah. And does it match with what we already got?
Yes.
Yes,
Yes,
ma'am.
ma'am.
Yes.
Yes, ma'am.
Y is determinant of
Second row.
1, 4 minus 1, 1, 2, 3,
1, 2, 3, 0, 5, 1.
0, 5, 1. Okay, this should be minus 22. Let's expand
Yes,
along
ma'am.
the first row. 1 times 2 minus 15 minus 1 times 4 plus 5 minus 13 minus 9. That's minus 20.
22.
That is determinant of
1.
1 minus 1, 4 minus 1. Here I'll have 1, 2, 3. In between I'll have 0, 6.
1.
So first row again, 1 times 18 minus 2 plus 1 times 4 plus 6. 18 minus 2 is 16 plus 10, 26. Does it match? Yes.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
So we can find the solution in 2 different ways. Do we know a third way to find the solution?
Gaussian
RREF.
elimination.
Yeah, the Gaussian elimination. So my matrix now is, I'll take the augmented matrix. So that's going to be 1, 0. What was the last row? 0, 5, 1. 0, 5, 1. 4 minus 1, 6, 1. 1, 2, 3. I'll convert this into RREF or REF and find the solution. So let me quickly do that. R2 is R2 minus 4R1.
4 times R1
R3 is R3 plus R1.
plus R1.
1, 0, 0, 1. 4 minus 4, 6 minus 0, 5 minus 0, 2 minus 4. Minus
2.
Minus 1 plus 1, 1, 1, 4. If the determinant of the matrix is not equal to 0, how many dependent variables will I have?
0.
3.
Sorry, 3.
Means 10.
All the
Dependent
variables will be independent.
Yes.
Right. So I can divide R2 by 6. I get 1, 0, 0, 1. 0, 1, 5 by 6 minus 1 by 3. 0, 1, 1, 4. Is this matrix an REF now?
No, ma'am.
No, ma'am.
No.
No, ma'am.
Pivot. Below the pivot, it should be 0.
R3 minus R2.
R3 is R3 minus R2. So that's going to give me 1, 0, 0, 1. 0, 1, 5 by 6 minus 1 by 3. 0, 0, 1 minus 5 by 6, 1 by 6. 4 plus 1 by 3. 12 plus 1, 13 by 4. Okay, we have definitely done something wrong because the answer is not 26. Or is it 26? No, right? 6 into 13 by 4. No, then something is wrong.
Ma'am, it should be 3, no? 13 by 3.
3 is it? Oh,
13
okay,
by
okay.
3.
Yes,
Fine,
ma'am.
fine.
Then it would be 26.
Okay. So now it is an REF. We can stop here and find the solution.
No,
1
ma'am.
by
It's
it's still
in
not in
REF.
REF. Okay.
Yeah. R3 6 times R3.
R3 is 6 R3. So that's 1, 0, 0, 1. 0, 1, 5 by 6 minus 1 by 3. 0, 0,
0, 0,
1,
1. 26.
26.
So we get the value of Z directly, 26. I know Y plus 5 by 6 into Z is minus 1 by 3. So I'll get Y is equal to minus 1 by 3 minus 5 by 6 into 26. This is 3, 13, minus 65, minus 66 by 3, minus 22. X is 1. X doesn't depend on any of the other two variables.
Excuse me, ma'am.
Yeah.
Ma'am, to convert this matrix into REF, diagonal elements must be 1.
Yeah, they are the pivots, right? The diagonal entries are the pivots. They have to be
So
1.
they must be 1.
Yeah.
Excuse me, ma'am.
We have only one method for getting the inverse of matrix, or any other method also?
We'll do the Gauss-Jordan method also. I'll tell you what that is.
Ma'am, can you
Means you
please
know that.
scroll up, ma'am?
Ma'am, I have a doubt in dimension rank.
Little bit, ma'am.
Yeah, I'll get to those doubts. We'll first finish these.
Yeah, I have doubt in. Just scroll up, ma'am. Here. How do you get minus 22 here, ma'am?
I'm just multiplying these two matrices.
Okay, ma'am.
Minus 9 into 1 plus 1 into 2.
Okay, ma'am.
So this is one way. You can also convert this matrix into RREF. Go one step further, convert it into RREF to get the solution, right? Is it already in RREF?
No.
Yes.
No, ma'am.
There's a pivot here, and above the pivot there is a non-zero entry. That's not okay. So what do we do? How to get rid of that?
R3 multiplied by 5 by 6.
Yeah, R2 minus 5 by 6.
5 by 6
R3. Yeah. 1 0 0 1 0 1. 5 by 6 minus 5 by 6 is 0. Minus 1 by 3 minus 5 by 6 into 26. Can you see that this is the step that is happening when we are doing RREF?
Yes, ma'am.
Yeah. So that's going to give me minus 22. So minus 22 and R3 remains as it is. So we get the answer directly.
In RRF, you can directly get the answer.
Yeah, x is 1, y is minus 22, z is 26.
Answer is same.
Yeah, it will be the same, no? It's a unique solution. So it has to be the same across whatever method you choose to solve the problem, right?
Okay.
So is this clear to everyone?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Clear.
Let's just find the inverse of the matrix. This matrix inverse we already found out. Let's find it using the Gauss-Jordan method. So in the Gauss-Jordan method, what do you do?
Did we have that Gauss-Jordan method?
It's your wish what you choose to find the inverse with. It means everywhere it is your wish, right? You choose which method you want to use to find the whatever solution or inverse or anything, right? But
answer will be the same.
It is going to be the same across all. So you can choose which one is easier for you. So in the Gauss-Jordan method, you will write down the matrix like this. You will write down A, and then you will write down the identity matrix by the side. And then you will do elementary row operations and convert A into the identity matrix. And whatever you get on the right will be the inverse of the matrix.
And so we have to do normal row operations on the A matrix for getting
So
it.
when you do it on A, you will be doing it on I as well.
Yes. Okay.
So it will be like this: 1 0 0 minus 4 6 5 minus 1 1 1 I identity. Now you will perform elementary row operations on this matrix. R2 is R2 plus 4R1. R3 is R3 plus R2. R1. So 1 0 0 1 0 0, and then you'll have 0 6 5 0 plus 4 1 0 0 1 1 1 0 1. Whatever elementary row operations we do here, you'll be doing the same on this part as well.
Okay, ma'am.
Yeah. And then the next, so this pivot is done. And then I have to divide R2 by 6. I'll do it here straight away. I have done R2 is 1 by 6 R2 also on this matrix. So I'll make this 1, 6, 2 by 3, 1 by 6. Fine?
Ma'am?
I've done one extra operation.
Ma'am? Rather than dividing, can we use R3?
You can interchange as well, no problem.
That will be easy, I guess.
Yeah, I think, okay, that'll be easier. Let's do that. R2 you interchange with R3. 1 0 0 1 0 0 0 1 1 1 0 1 0 6 5 4 1 5. And then we
But
want
ma'am,
to
in this case, I think the inverse is not exactly the inverse of the, I mean, the base matrix.
no, you will get the same. I'll show you.
Oh, okay.
R3 is R3 minus 6 R2. This is a pivot. This is a pivot. 1 0 0 1 0 0 0 1 1 1 0 1 0 0 6 so minus 1 4 minus 6 that's minus 2 1 0 minus 6. So let me skip one step and multiply it with minus 1. I'm doing that. So I have pivot, pivot, pivot. I still haven't converted this portion into the identity matrix, right?
Yes, ma'am.
Yeah, this entry has to be made 0.
R2 minus R3.
Yeah, R2 minus R3. 1 0 0 1 0 0 0 1 0 1 minus 2 is minus 1 0 plus 1 1 minus 6 is minus 5 0 0 1 2 minus 1 6. So is this the inverse that we got earlier?
Yes.
Yes, ma'am. Yes, ma'am.
I hope so.
Yes, ma'am. Same.
Oh, that's not what we got. Minus. Oh, we've got something
Ma'am,
here.
you have taken another matrix. You have taken
Oh,
minus
did
4?
I take another matrix?
Yes.
1 0 0 4 6 5 minus.
You have taken minus 4, I think.
Oh, okay, fine.
No issue.
So you will get the same inverse.
What is this? What is this process known as? I have never seen it.
It's there in the video lecture. No, this is called the Gauss-Jordan method of finding the inverse of a matrix. You'll be using the Gaussian elimination. That's right.
Okay,
No, it's
this
your
is
choice.
like augmented version.
It's your choice. If you're comfortable with the adjoint of the matrix.
I have done it with individually using this row reduction.
Okay.
Ma'am?
Yes.
Ma'am, if we have two square matrix and when we multiply, suppose you take A and B, when you multiply A with B, you'll get an identity matrix.
Okay.
Then can you say that
yes,
A is the inverse of
that.
B?
Yes.
Can you repeat? Oh, yeah. Yeah. Okay, yeah.
Yes.
Please repeat.
When we multiply two square matrix, and if we get an identity matrix, then can we say that B is always inverse of A?
Yeah, if A is a square matrix, yes.
A and B both.
If A is a square matrix, obviously B has to be a square matrix, no? For it to be identity.
Okay. Then we can also get that BA is also going to be
identity.
I.
Yeah.
Okay, and for A, I mean B is always unique to get identity.
The inverse
matrix.
of a matrix is always unique. Yes.
Okay. And suppose we have three matrix, then we can say that AB is inverse of C, and A is inverse of BC as well.
C inverse is equal to AB, right? And what else did you say? BC. Yeah.
BC is also.
Yeah.
But
you
in
cannot
this
tell
case we
anything
can
about B.
AC. We can't say that AC is inverse of B.
No.
Okay.
Because
okay.
we know that AB need not always be equal to BA.
Yes, exactly. Okay,
Yeah.
ma'am.
Okay, any other questions? We cover everything.
No, ma'am. Zero. No.
All clear, ma'am.
Yeah, someone had a doubt in activity.
And rest of the topics we will take tomorrow, ma'am.
What is it?
And rest of the topics, ma'am.
You want me to stop now?
No, ma'am. I am asking, ma'am.
together.
I am asking. You were saying that this is the last topic. Then after we will take queries.
No, for these two. We'll get into vector space after this.
Okay.
I think we have
Hello,
covered it.
madam. I have a doubt. Like there was a lecture, like in homogeneous system of equations, there are more variables than equations. Then it is guaranteed to have non-trivial solutions. Means what does it mean? Means, can you give its example?
Can you please repeat that?
In a homogeneous system of equations, if there are more variables than equations, then it is guaranteed to have non-trivial solutions.
Yeah, right. So what is a
Yes, what does it
homogeneous
mean?
system of equations? We forgot this. What is a homogeneous system?
Ax equal to 0.
Yeah, when B is equal to 0, it's called a homogeneous system. This system always has a solution, right?
Yes, ma'am.
Yes, ma'am.
Can you tell me one solution?
Zero.
One type of solution is trivial, and
Trivial.
another is
0, 0, 0.
infinite.
Zero or infinite.
Many.
Infinite many
It's just a unique solution.
Infinitely many.
That is the zero solution, or there are infinitely many solutions.
Yes.
Okay. So now you have a rectangular system when the number of equations is more than the number of variables, right? Is that what you said, ma'am?
No, more variables than equations.
Okay, fine. So I have two equations and three variables. Can you see that the maximum number of pivots I can get in the matrix is 2?
Yes, ma'am.
Yes, ma'am.
The pivots come from the rows,
Yes, ma'am.
right?
I don't understand what are you saying.
So 1, 1, 1, 0, 1 minus 1, 0, 0. This is my matrix form, right? Augmented matrix. Yeah.
Yes.
So how many pivots can I have? Can I have more pivots than the number of rows?
No, ma'am.
Two pivots.
Yeah, you can have only two pivots, right? But there are three variables.
Okay.
Which means that at least one of them is independent, right?
Okay. Right.
That's why it will have infinitely many solutions.
Okay.
Any other doubts?
Ma'am, how can we after seeing the question, how can we tell that it has unique solution, one solution, or no solution like that?
Just by seeing, if you have the geometrical representation, you can tell based on whether it is intersecting or not. Two lines, whether they intersect, whether they are parallel, or with that you can tell. But then otherwise you have to do this, convert it into augmented matrix and then RREF. REF is enough.
Ma'am, if we initially see any row or column as a product of something, then can we determine roughly what is the rank or what is the dimension, like things, or what will be determinant in basic standards?
Can you please ask that again? You write a row as?
I mean, if by seeing the question itself, if some row or product means row or column is a product of each other.
Yeah. Like
Then
the first
can
matrix
we
that I wrote, right?
estimate the determinants and its characteristics?
Yeah, in this case, the determinant will be 0, right?
Yeah, in this case, it would be 0 and only one row is multiple of others. So other things would be following.
Yeah, so what is the question? Yeah, we can tell that the determinant is 0 because one is a scalar multiple of the other. A row is a scalar multiple of the other. So in this case, the determinant will be 0, right?
Yes, ma'am.
So I will either have a no solution case or infinitely many solutions case.
Madam, in above you read that x plus y plus z, that augmented matrix. In that, can we have one means one dependent variable?
One dependent variable. Yeah, why not?
No, you said two for that equation, two dependent and one independent.
No, at least one independent. That is guaranteed, right?
No,
in this case, there is one one independent variable.
Yes.
But what I said was at least one independent variable is guaranteed. At least one.
Okay.
See, if my second equation was this 2, 2, 2, then after I do RREF, I'm going to get this, right? Not RREF, REF. Okay, this will also be in RREF.
Yes.
In this case, I have only one pivot, right?
Yes, one dependent and two independent.
Yeah. So when I have more variables, I'm guaranteed that there is at least one independent variable. I'm not telling exactly this, how many independent, but I'm guaranteed there is an independent variable. Because the number of rows is the number of maximum number of pivots you can get is the number of rows of the matrix, right?
Okay, ma'am.
Ma'am, one question. For homogeneous system, if the matrix is a square matrix, then by looking at the determinant, if it is 0 or it is non-zero, what can we say?
So if the determinant is not 0, whether it is homogeneous or not homogeneous, you know there is a unique solution, right?
Yes.
When the determinant is 0, we had two options. No solution, infinitely many solutions. But no solution can never happen for homogeneous system, right?
Yes.
Because I always know that there is x is equal to 0 as a solution. So it will be infinitely many solutions.
Okay, ma'am.
Ma'am, I have a doubt in activity 4.2, question number 4.
4.2.
Yes, ma'am. May I ask this or not?
Okay, fine. Okay, maybe we will take a 5 minutes break, kind of, where we will be solving activity question doubts.
Yes,
And
ma'am.
then-
Yes, ma'am.
Yeah.
Okay.
Again, we'll come to the definition of a
Okay,
vector
ma'am.
space. Or maybe we'll do one thing. Let's stop discussing concepts. Let's take whatever doubts you have.
Ma'am, but we need to discuss vectors, ma'am. That is more important.
Okay, fine. Okay, we'll do.
So that will take time also, I think.
Ma'am, if we go sequentially,
Huh?
if we
Ma'am,
go sequentially,
whatever we have revised so far, you can discuss the questions from that part only. And after that, you may, if you wish, you can discuss.
Okay, then we'll proceed with our original plan only.
Yes, ma'am. That is fine, ma'am.
Okay, and then once we stop the session, whoever has doubts can stay back and get the doubts clear.
Yeah.
Anyway, there's a session tomorrow, so no problem. Yeah. So, yes, what is a vector space? What is a vector space?
It is a set
With two operations.
with two operations, addition and scalar multiplication.
Yeah.
Satisfying
You have a
the-
set and an addition defined on it and a scalar multiplication defined on it. Only that triplet can be called a vector space. You cannot tell that a set is a vector space or not. The question of what is the addition, what is the scalar multiplication is what plays the key role. So a set with an addition and scalar multiplication is said to be a vector space if it satisfies 10 conditions. Can you quickly tell me what are the 10 conditions?
Closer to the addition.
Yeah. You pick any two elements from the set, you add them, it should be in the set. And then
scalar multiplication also closer to
you multiply. You take any element from the set, multiply it with a scalar. Scalar means real number. The product, the output, should be an element of the set. Then
Addition should be commutative.
yeah, x plus y should be equal to y plus x for whatever x and y you take. It will also be associative.
Associativity should be there.
And then
Zero vector should be there. So x plus
there
0
exists,
is equal to?
yeah, there exists a zero vector which acts as the additive identity. And then
Inverse.
Additive inverse.
yeah, there is an additive inverse. There is a vector with which when I add, I get the additive identity. And then
Unity.
1 into v is equal to.
yeah,
Unit
1 into
vector.
x should be equal to x. And then
A plus b into x is equal to
alpha beta into x should be alpha into beta x. Alpha plus beta into x should be alpha x plus beta x.
Beta x.
And then
Alpha into x1 plus x2.
x1 plus x2.
right. Distributivity, 2 properties about the scalar multiplication, 4 properties about the addition, closure properties. So if all these 10 conditions are satisfied, then a vector space along with this plus and dot is said to be, means a set to be along with this plus and dot is said to be a vector space. So if you are given a set and asked to check whether it is a vector space or not, you should make sure that you check every condition and all the conditions are satisfied. If you want to say something is true, take a general element from the set and prove that it is a vector space, means it is satisfying all these conditions. If you want to say any one of the properties is false, then pick any set of vectors that does not satisfy any of these properties. Like for example, if you want to say this is not satisfied, if you want to show it is satisfied, you have to pick a general element and show whatever x and y you take and you add, it is equal to y plus x. If you want to say it is not satisfied, you just pick some random number and show that for that it is not satisfied.
Ma'am, just one
Yeah.
query. If question asks for vector space proving or checking whether it's a set of elements forms a vector space or not, then all the 10 conditions are required.
Yes.
Otherwise, if it asks for subspace, then only 3 are required, including 0, 0.
Yeah.
Okay. And in vector space, is 0, 0 required?
The 0 element need not be the 0, 0. So whatever the element that is acting like this, that is the element you need to look at, not necessarily 0, 0.
Okay.
We have examples, no, that 1 comma y, that set, their addition and scalar multiplication is defined in a different way. For that, this is the 0 element. So depending on what the addition is, what the scalar multiplication is, the 0 element will also change.
Ma'am, say for any question, there are 4 options. So for all options, we have to check all the 10 conditions. So we have to check 40 conditions. Then.
10 for each. If I give you 4 sets, then you have to check whether each one is a vector space. You have to check all the 4. Means for each one, you have to check the 10 conditions.
Yes, ma'am, but there should be a technique to come up with.
No, there is no shortcut to this. All 10 conditions. So
generally,
there is no way we are going to ask something like that.
Yeah, ma'am. But generally, what we do, we pick up some element example and then we check for this condition.
No. You cannot pick elements and say that it is satisfied for this, so it is
No,
satisfied.
which is satisfying in that vector space. Okay, ma'am. When you do the question,
I think that is true if we want to prove false.
Yeah,
I mean,
for false,
not
you
a
say
vector
something is false, you pick some random element and then check whether it is holding or not. But not when you want to say it is true. When it is true, you have to pick general elements in the sense that how will any element in a vector space look
okay,
like?
we will see with examples.
Yeah.
Like we can pick xy as well, if we consider for R2.
I'm thinking of an example. Okay, you know Rn is a vector space, right? Rn, just the zero element. All these are vector spaces, right?
Yes, ma'am.
Set of all m cross n matrices. So let me construct an example. Okay, let's take this set only. This is a set. This is a subset of R2. I'm using usual addition and usual scalar multiplication. So now, is this a vector space?
No, ma'am.
No, ma'am. It is not, which means at least one of the 10 conditions is not satisfied, right?
Yes, ma'am. It's not closer to R2.
Okay, it's not closed, but let me pick this condition so that.
Ma'am, can you explain how it is not closed and from basics for one question?
Yeah, I will.
Then if
So,
the addition is defined, then we can say it is vector space. Here it is
yeah,
usual
yeah.
addition. That's why we
If
are
we
calling
change
it.
the addition, yeah, if we change the addition, it will be a vector space. This has been discussed in my week 3 live session, so you can go back
Yes,
and
ma'am.
watch.
Yes, ma'am.
Yeah.
Yes,
So
ma'am.
now let me show how this is not closed under addition. How will any element in this vector space look like? In this set look like?
First element should be always 1.
First will always
First
be
element should
1.
always be 1.
Yeah. Second is going to be something like this. When I add these two,
Real
what will I
number.
get?
And 1 comma 1 could be also there, no?
2 comma.
Okay, fine. 1 comma 1. When we add these two, what do we get? 1.
2 comma 3.
2 comma 3.
Does this belong to this set?
No.
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 No, ma'am.
No,
Because the
ma'am.
first element is 2, right?
Yes, ma'am.
Yes.
This condition is not satisfied. I've just picked 2 elements, right? Because I want to say something is false. It's enough if I show just for these 2 elements it is not holding, right?
Yeah.
Okay. If question is given like if there is condition given like 1 comma 3 is addition, 1 comma x is addition, then only we can say it is a vector space.
Yeah. So now I define addition as 1 comma y plus y1 comma 1 comma y2 is equal to 1 comma y1 plus y2. Now I cannot say that 1 comma 2 plus 1 comma 1 is equal to 1 comma 3. 1 comma 3 belongs to the set, so it is closed under addition. You cannot say like that. For this set it holds. For these 2 elements it holds. But there may be some element where it does not hold also, right?
Okay.
So when you want to say something is true, you have to pick in general. One comma y1 plus y2. It is of this form again. So this condition is satisfied. Here it is not satisfied, so I picked numbers. Is it clear?
Yes, ma'am.
Yes, ma'am.
Ma'am,
So I want to say all human beings have 2 eyes. I cannot
can
pick one human being and say that this person has 2 eyes, so everyone has 2 eyes, right?
Yes, yes,
Okay,
yes.
assuming that everyone has 2 eyes is a true statement.
Ma'am, for this vector to be a vector space, we need to define multiplication also.
Yeah. I no, I was just defining for the closure property of addition, so I didn't do it.
Okay.
Ma'am, I have a doubt. In the above example, you did 1 comma 2 plus 1 comma 1 is equals to 2 comma 3.
Usual addition.
But
component wise.
If we are putting the first one is fixed, so we can't add 1 comma 1, no? 1 and
No, I am
1.
defining addition like that. I am defining that if I want to add any 2 elements from this set, this is how I will add them. That's how I am defining.
Okay. Because v is equals to 1 comma y you are saying, so if we are adding the 2 elements, so first one is fixed, so we are not going to add it now.
No, that's how you're defining addition. See, why are you adding like this? Because you were taught like this, right?
Right.
If you were taught like this, you would say this is correct, right? So that's how you're defining addition.
Okay.
You're changing the definition of how you add two vectors.
So we are putting the condition 1 comma y.
Ma'am, for solving any question to find if it is in vector space or not, we should always take in the variable form like 1 comma y1, and then we should generalize it and check it in the closure or
If you know that it is not going to belong, then you can take numbers. Like this. You know this statement is not going to be true, then you do this. Numbers is okay.
Okay.
So if I want to say that every human being has two eyes is a false statement, assuming it is a false statement, then if I show one human being who does not have two eyes, then I'm done, right?
Yes, ma'am.
Yes, ma'am.
Say, for example, every human being has two heads. That's a false statement, right?
Okay.
Is it necessary for me to prove that every human being does not have two heads?
No.
If I just say I have only one head, I am a human being. So the statement is false, right?
Yes.
Just by giving one example, you can say that a statement is false. But every human being has two eyes cannot be proved by telling that I have two eyes.
So if I get only one example that is false, then it is false.
The statement itself is false.
Yeah.
But one example that is true is not going to tell the statement is true. Any questions on what a vector space is? Okay, then maybe we'll move on to subspace. Where do you want to stop? Shall we stop at subspaces so that linear independence, span and basis will be discussed tomorrow?
Hello, ma'am.
Yeah.
Can I ask activity question related to this, ma'am?
Yes, sure.
Yeah, one second, ma'am.
Yeah. So shall we stop at subspace and tomorrow continue with the linear independence, dependence, span and all that?
Yes. Yeah. Okay, ma'am.
Yes.
Yeah, but
It will be good.
too much content for one
Yes, ma'am.
thing.
Yes.
So tomorrow I'll ask Subhajit to start from vector space again. Vector space.
Ma'am,
subspace.
can we have a summary like if matrix by looking at matrix the linear dependence, linear independence,
You should write the summary and put it on Discord so that everybody benefits.
I always have confusion related to this, so that's why I was thinking that if it is in the revision, then it will be easier.
What linear dependence, independence, and determinant?
Linear dependence, linear independence, independent variable.
No, you shouldn't confuse linear independence, dependence with independent variable and all that. That's different. This is different. Independent variable, dependent variable comes in the context of RREF.
Yes.
So that's different. This is different. That has nothing to do with determinants. Independent variable, dependent variable, and all.
Okay.
Hello, ma'am.
Yes. What is the now?
See, actually, it was asked as part of the grade 5 assignment only. 1 minute, ma'am. See, actually, they have given like. Shall I tell the question number?
Is at 6. Yes. Yeah. Question number.
It was graded assignment 5, question number 4, but it is also related to the dimension of the vector space only, ma'am. So.
Graded assignment 5.
Fourth question, ma'am. See, they have given like from 2 dimension to we are. The function is defined as from 2 dimension to 2 dimension, but say for example, like a 5 modulus x comma 0 is not taken, is mentioned as a wrong, I mean, it's a wrong answer. So can you just define how, when we are like transforming from multiple dimension to, say for example, single dimension, or from single to multiple dimension, how do we take, I mean, here they have told that first answer is wrong. So I don't understand how, because when we
No,
just
why
look
are
at
you
the
studying all
vectors,
this? This is not there for this quiz one.
no, I'm just
What is
asking in general, like when we are converting from, I mean, even in, I mean, as part of the fourth, that is week 4 and all, when we are trying to change from multi-dimension, say for example 3 dimension to 2 dimension, but the function has been
What are
defined
we trying to
properly.
change?
We don't have transformation.
We don't have functions at all, no? We don't even have transformations in the syllabus. Why are you
As
changing
part of
from
the
2
week
dimensions?
4.
No, we don't have any functions in week 4.
Okay, we don't.
Let's discuss after quiz.
Okay, I'm sorry. No, actually, I've seen similar questions. I'm also part of MLF, so similar questions were asked. So that's the thing I asked as a general question. Like when we are trying to transform from one dimension to another dimension, and if it is defined properly, but how do we determine that the particular, say for example, vector doesn't fall into that dimension vector space? So
Okay,
y-
I
you're not
didn't
getting my
understand your
question.
question. Yeah,
Okay, ma'am.
but one
Maybe I
thing,
think today it's too much. Maybe I'll prepare that question and in the next class. Or when will be the next class, ma'am?
tomorrow, 6.
Okay, so I'll just ask because I think a similar question has come in MLF also. So I just got confused.
Yeah.
But
See,
it's a
MLF you
generic
will have,
question like,
obviously, because
yeah, it's
it's an extension of this.
yeah, so it's a generic question actually for me. Like when we are going from one single dimension, one particular dimension to different dimensional space, and this type of vectors like say 5x comma 0 is not considered as that dimension. So
Mm.
I mean, is there any generic rule to
No,
determine
what
like,
is 5x comma 0 is not considered as an element in that space? What does that mean? This belongs to
no,
R2, right?
yeah, but when I've chosen that answer, it is mentioned as wrong, so that's why I asked, ma'am.
No. See, you should go back and see what the definition of a linear transformation is. Do that only after the quiz, not now.
Okay, ma'am.
That's not there in the syllabus. So,
Okay, ma'am. No,
yeah,
but I asked this as a generic question, so that's
yeah,
fine, ma'am. Maybe I'll ask next time, ma'am, during the 5. Okay,
normal
ma'am.
session. Yeah.
Sorry. Yeah. Thank you, ma'am. Sorry.
So, yes, what is a subspace? When do you say something is a subspace?
When there is a
Any
generator
subset
and
Subset of a
of
vector space, subspace, which stands.
It is a subset of some bigger vector space, and it is a vector space in itself, right? Means
Right.
as a set, W is a vector space, and in addition to that, it is a subset of some bigger space. And because of this being a subset of a bigger vector space, out of the 10 conditions, you just need to check 3 conditions. One is whether 0 belongs to W, then whether it is closed under addition, and the third is whether it is closed under scalar multiplication. So if these 3 conditions are satisfied, then you can say that W is a subspace of the vector space V. It should be with the same addition and same scalar multiplication that is defined on V, not different addition, different scalar multiplication and all. Am I audible?
Yes, ma'am.
yes, ma'am.
Yes.
Yes, ma'am.
Just the 3 conditions for checking if something is a subspace or not. So is this
X plus Y should be in W only, no?
yeah.
You said V. What you said?
Oh, did
X
I
and
say
Y
V?
should be from V.
No. You take elements from W, you add them, the output also should be in W.
W. Yeah.
Okay. So we saw this, right? Y1 comma Y, where Y was any real number. Is this a subspace of R2? Under
No,
usual
no,
addition?
ma'am. No,
No,
ma'am.
ma'am.
No, ma'am. Because zero vector doesn't exist.
Again, its addition is not closed.
Under usual addition, addition is not closed. So this is not even a vector space.
Yes, ma'am.
Yeah. Now we redefined addition. We redefined addition as something. Addition is defined as 1 comma y1 plus 1 comma y2 is equal to 1 comma y1 plus y2. Now is it a subspace?
No,
no,
Zero
ma'am.
is not there.
Zero vector is not.
You should check with respect to the. Now, if you want to talk about subset of R2.
Ma'am, want the 1 comma 0 will be the 0 of this vector space?
Yes, it will be. But then, is R2 a vector space with this operation? That also you should check, right?
Okay. No. Then R2 is not a
I
vector
do
space.
not understand. No,
Okay.
this last part what you said, R2 is.
No, you ignore this then. I know it will be confusing. No, see, what I was trying to tell is R2 a vector space with respect to this addition?
This is what you have defined already.
I am defining addition like this.
Yeah.
Is R2 a vector space with respect to this operation?
No, ma'am.
Why not?
There is no zero.
No, but then this will act as 0, right?
It will change accordingly.
1 comma 0. Yeah.
It will belong to R.
Multiplication.
And for R2, 0 comma 0 only will be the 0.
No, it depends on
general.
what the operation is.
No, it's 1 comma 0. What about multiplication? In what way?
Multiplication you will define, no?
Alpha 1 comma
alpha y.
Alpha y.
Then it is a subspace.
Then it is a vector space, ma'am.
It is inside. No? It is a subspace then, I think.
Ma'am, it is a subset, but it's not a subspace.
Why? This is a vector space. No, we showed earlier, no? This is a vector space with respect to these operations.
Addition 0 and a scalar multiplication conditions would only be satisfied. All are satisfying there. So it is a
but ma'am,
but the question is R2 a vector space with respect to these operations? Only with respect to the same operation, I can tell whether it is subspace or not, right?
Ma'am, I didn't get what you were saying. Can you please repeat?
No, I think we'll just ignore this. I don't want to confuse you people. Let's just ignore this.
Ma'am, is this not a subspace?
It is a subspace. It is.
Ma'am, is it a vector space or not, ma'am? Yes, no.
Ma'am, subspace of what?
It is a vector space.
Yes, ma'am. Okay.
Subspace of what, ma'am? Of
subspace
R2?
of R2 with respect to this addition and this scalar multiplication.
Okay.
No, you ignore this. So I was unnecessarily complicating things. That's not what we do in revision session. So let's ignore that. Yeah. So shall we do some examples of subspaces? Now, if I take the set of all matrices, say n cross n matrices, satisfying the condition that determinant of the matrix is equal to 0. What is this a subset of? Can you tell me a bigger vector space which you know for which this is a subset?
A matrix, all set of matrices.
Set of all.
Square matrices.
Yeah. So now, is this a subspace or not?
Yes.
Yes, ma'am, it is.
Does the zero matrix belong to this space?
Yes, ma'am.
Yes.
Because determinant of the zero matrix is 0.
Yes, ma'am.
Now, if A belongs to W, then I know that determinant of A is equal to 0.
Yes, ma'am.
What can you tell about alpha A? What is determinant of alpha A?
Alpha
0.
Alpha N A.
So alpha A also
0.
belongs to W. Now, if A comma B belongs to W, I know determinant of A is 0, determinant of B is 0. What can you tell about A plus B?
We could not say from.
No, ma'am.
But
Determinant
A plus
of
B
A is
is
not
equal
equal
to
to
0?
determinant of A.
Yes,
No,
We can split it.
because A and B both are 0. No?
No, ma'am.
No, I told you, no, this is not equal to determinant of
Yes,
A
ma'am.
plus determinant.
Okay.
Yes.
So this is not closed.
Yeah. So can you give me a set of matrices for which this does not hold?
Yeah, one is
I gave no in the initially.
one
Is
is A and other is
identity
minus
matrix,
A.
another is minus identity.
Minus A.
We want determinant.
No, ma'am. 1 0
0.
0 0 we should take. Yes, ma'am.
B is
Minus
equal to,
1.
we can take this.
0 1.
Right? What is determinant of A plus B? What is A plus B?
1 0 0 1.
Identity matrix, right?
Right.
1.
Its determinant is 1.
Yeah.
Yes, ma'am.
So A plus B does not belong to this. So you have to check all the conditions. Just because these two were satisfied, you cannot think that the third one is going to be satisfied on its own.
Ma'am, can you mute all?
Mute all. Okay. Okay. Then what else? Can you tell me some other example of subspace?
Ma'am, can you please tell me that proper subspace?
Proper subspace. Proper subspace just means that this is a proper subset. That's all. V is a subspace of V.
Yes.
V is a vector space. It is also a subset, improper subset. So it is true. Proper subspace means you're not talking about V. That's all.
Ma'am, I don't understand. Actually, there in mock the question. Can you take that question? Means that
Yes,
only
ma'am.
option.
Please
Okay,
take
so we
that
will
question
stop
and-
content here and we'll just do doubts.
In mock,
I asked the doubt, but
in
We'll take
mock
down
question. Question 6 in mock and second option. Can you explain that option?
Ma'am, may I leave, ma'am?
Yeah, sure.
Thank you, ma'am.
Is my screen visible?
No, ma'am.
No.
Yes, ma'am. I will just leave the call and join again. I'm not able to share screen. Just come back in a second.
All right, ma'am.
Is my screen visible now?
yes, ma'am.
Yes, ma'am.
So what was the question?
Question number 6, option second.
Span of S is a proper subspace of R3. If you get span of S is equal to R3, it is not going to be a proper subspace, right?
Then means what, madam? What?
First, what
Proper
meaning
subset.
for proper subspace, ma'am?
Ma'am, actually
Proper
I forgot.
subspace means it is a proper subset, and which is a vector space.
Ma'am, actually I forgot what is proper subset. Can you explain that also?
1, 2, 3. What are the subsets of this set?
1, 2, 1,
1, 2, 3,
set.
1, 2, 2, 3, 1, 3.
2, 3, 1, 2, 1, 3, 2, 3.
2 3.
1, 2, 3 itself.
How many proper subsets are there?
1 2 3 4
8.
2 is to n minus
2 to the
1.
power n minus 1.
8,
All these are proper subsets, right? This is the
7.
set itself. This is
7.
called an improper
Okay.
subset.
So we should leave that particular set.
So V is a subspace of V. That is obvious because V is a subset of V and V is already a vector space, right? So V is always a subspace of V.
Yes, ma'am.
Leaving all that, every other subset is a proper subset, and if those subsets are vector spaces, they are called proper subspaces.
Okay. But don't we have to check the conditions? Means that 3 conditions.
So you have, what is span of S? Span of S is the subspace generated by this, right?
Span of S is vector space R3.
You're getting R3, no? Then span of S is equal to R3. Then it is not a proper subspace, right?
No, madam, I am not understand.
What are the
ma'am,
subspaces of R3?
0, 0, 0 vector.
With three components.
Lines passing through the origin, planes passing through the origin, and R3, right?
Yes.
These are the subspaces of R3.
Okay.
Is this a proper subspace of R3?
No.
Because R3, the subset of R3, it is actually equal to R3. This is an improper subset, right?
Yes.
Is this a proper subset?
Yes, ma'am.
Yes.
Yes, ma'am.
Planes. It's not R3, no. Plane is not R3, right?
Yes, ma'am.
Is this a proper subset?
Yes, ma'am.
Subspace?
Yes.
This is a proper subspace. So you're getting span of S is equal to R3, right? So this is span of S, right?
Yes.
So is it a proper subspace?
No.
Proper subspace means it would have either been a plane line or the zero vector, right?
So span of S is equal to R2. That is okay, ma'am. It's a proper subspace of R2.
Span of S is equal to R2 is a proper subspace of what?
Instead of R3, I'm saying that it's R2. Is that statement is true then?
No, subspace of what? What is the bigger vector space?
R3.
No, you cannot talk about R2 being a subset of R3, right? Because
Okay.
R2 elements have only two components, right?
Yeah.
Here you have three components.
Three components.
This is not a subset of this.
Okay.
But any
Suppose
element
you
which is in the
say
form of
add,
x
you
color
add
y,
the XY plane, then it is a
cannot
proper
span.
subset.
Yes, ma'am.
Yeah.
Ma'am, then can we understand like this, and any element which the particular is not a proper subspace?
Any element?
With that particular R2 or R3, whatever it is, then that particular span is not a proper subspace.
If it is equal to R3, it is an improper subspace. No, means it's an improper subset.
Span definitely will be equal, no ma'am, with that particular component. R2 means it should have two components.
Yeah, but what is the span of 1, 1?
It's R2.
It's a line. It's a
No,
line.
this is not R2. This is a line, right?
Line. This is the line, ma'am.
This is a line, Y is equal to X.
Okay.
And ma'am, this is a proper subspace.
Yeah, because it's not R2.
Okay. R2 means we need two directions. Okay, ma'am.
Yeah.
Ma'am, this is a proper subspace of R2.
Yeah.
Okay.
Ma'am, may I ask now?
Yeah, activity 4.2, right?
Yes, ma'am. Ma'am, I have this question only.
Which question?
Mock test 6, first option.
Okay, 1 second. Shall we finish this and get there?
Yes.
Yeah. So what is the doubt in 4.2?
In the question number 4, option 3. How V1 and
is
V2 will not be...
x-axis, V2 is y-axis. Option 3, V1 union V2.
Yes, ma'am.
Why is it a subspace?
How will it not be? Can you explain this?
No, you tell me what are the conditions you will check for a subspace?
The addition property and scalar multiplication property.
And 0.
Yes, ma'am, and 0 property. 0 vector.
Yeah. Say V1 comma V2 belongs to W implies V1 plus V2 belongs to W, and scalar multiplication. Alpha V1 belongs to W implies alpha V1 belongs to W implies alpha V1 belongs to W. Does the
here
0
B1
element
plus
belong to
B2,
this?
B2 doesn't belongs to that union part. That's why it's not.
Does 0 belong to the subspace? Whatever, V1 union V2.
It can be, ma'am, like if x is equal to 0, then...
It is there. It is there.
Yes, ma'am. Right.
Not can. It is there.
Yes, ma'am, it is there.
What about this one? Scalar multiplication.
Okay, for V1 it will be alpha x in alpha x 0, comma 0.
For V2?
0, comma alpha y.
It is there, no?
Yes, ma'am.
So it's okay. What about addition? Does 1 comma 0 belong to the union?
Like V1 plus V2, ma'am.
Does it belong
No.
to not V1 plus V2, V1 union V2, no?
Yes, ma'am.
Does 1 comma 0 belong to V1 union V2?
Yes, ma'am.
Yes, ma'am. It belongs.
Yes,
Does
ma'am.
0 comma 1 belong to V1 union V2?
Yes, ma'am. It belongs.
What about 1 comma 0 plus 0 comma 1?
No.
Does this belong
No,
to
ma'am.
V1 union V2?
No, ma'am.
That's all, right?
Okay.
Okay. Mock test.
And also I had this small doubt, like we are first learning that rank is same as dimension.
No. Please ignore that statement. Dimension is for a vector space, rank is for a matrix. Don't talk about rank of a vector space.
Okay, like in the week 5 we are studying that dimension of a null space.
That's different. Null space is a vector space. It is a subspace.
Okay.
So you can talk about its dimension, the number of elements in a basis.
Okay, but for
Ma'am,
like
rank.
but number of non-zero rows
Row
is also a
space.
dimension. Is also a dimension, and the dimension is also the rank.
No,
right?
that is
No,
rank of
Ma'am,
row
actually, rank of a matrix is same as the vector space containing the row space of that matrix, the dimension of that vector space. Yeah.
No, you ignore null space for now. You concentrate on
Yes,
dimension
ma'am.
of a
Yes, ma'am.
vector space. Yeah. And rank of a matrix.
Ma'am, dimension of a vector space is just number of elements in the basis.
Yes.
And the rank is same, right?
Rank of a matrix. Oh, no.
Rank.
See, you ignore rank of a vector space. There is nothing called as rank of a vector space. Means it is there, but you ignore it.
How to relate the matrix multiplication rank suppose A and B are two matrix. AB, what is the rank of AB? How can we know with the rank
It is
of
less than or equal to rank of the
Minimum of m comma 1 m comma n. No, ma'am.
That is also there. In terms of ranks of the matrices, it is this.
Okay.
Yeah, rank of any matrix is less than or equal to minimum of m comma n.
Ma'am, actually, it's just a theorem, but we don't know the proof of this.
No, it's simple, no? You have a matrix. How will you find out its rank?
Number of non-zero rows
in row
under,
echelon form,
yes.
right?
Yes.
So you will convert it into row echelon form. And then how many maximum non-zero rows you can have?
All the rows.
Maximum is m.
The number of rows, right?
Yes, ma'am. M.
Yeah, m, right?
Yes, ma'am. Ma'am, actually, I am asking about that rank of AB multiplication.
Oh, for that you have to do a little work. Yeah, it's not very straightforward.
So, ma'am, was it not there? I mean, in the week 5?
No proofs. This is a formula for you.
Okay. Actually, there is a question in graded assignment 5. So I just applied this formula. I don't know.
Yeah. Use it as a formula.
So will we get to know the proof of this?
We can after doing null space.
Okay, in week 6 or?
Yeah. In week 5, null space comes into picture, right?
Yes, week 5.
Yeah, after that you can prove this. Maybe in the week 6 live session, we'll do that.
Okay. I have also some doubts on that 1-1 function. So.
Yeah, we'll do all that later.
Okay, and ma'am, one more thing. Week 6 practice assignment deadline is on 16th. Quiz 1, I mean, on that day we have quiz 1. So.
Yes,
No,
ma'am.
it will be extended.
Okay, and the graded assignment deadline will also be extended or not? It's on 21, I think.
I think that will already be with the extended thing. I don't know. Shubhajit told he'll reply on the discourse thread. So maybe you just check that. He told me he has replied. So just check that thread maybe. If I don't know what he has written there. I was in the session, so he told he'll reply. Yeah, he has messaged telling he has replied. So maybe you could check that. Don't worry about all that. Yeah, mock question 6.
Ma'am, question number 6. Option 1.
Question 6, option 1. Okay, does
Yes.
7 comma minus 2 comma 2 belong to the span? What is span of a vector space?
Set of all finite linear combinations.
So can you write 7 comma minus 2 comma 2 as a linear combination of these 3 vectors? If yes, then it belongs to the span. If no, it doesn't. That's all.
Ma'am, I didn't get the solution of which is provided. So can you please
Why didn't you get the solution?
mock quiz solution?
It is there, no, here?
Yes. But I didn't get
Oh, you didn't understand
one.
what it is.
Yes.
Okay.
Yes.
1 minus 1 0. 1 minus 1 0 plus beta times 0 1 1. What have I written that you didn't understand? So if you are able to write minus 7 2 2 like this for some alpha, some beta and some gamma, then it is a linear combination, right?
Yes.
Means it belongs to the span, right?
Yes.
So this is alpha plus 2 gamma minus alpha plus beta plus gamma, right?
Okay. Right.
You are going to solve this system of linear equations. If you get a solution, fine. If you don't get a solution, it means you cannot write as a linear combination, right? Check if the system has a solution. That's all. Right?
Okay.
Yeah.
Ma'am, we can also check that those 3 vectors are linearly independent or not. If it is independent, then the basis, I mean, span
You are
set
trying
is
to show
R.
that span of S is R3. If you do this, then it means you can write this. Oh, that's what I had written in the solution, right?
Yes.
Yeah.
But there you were assuming that we want to show it like is equal to R3. Right.
Yeah. If you show this, then you can write this as a linear combination. If you're doing this, you're not worried about what the span is. You're just checking that this belongs to the span or not.
Okay.
Ma'am, can you please again explain the subspace question of this options?
This one, right?
Yes, ma'am.
It is just x-axis union y-axis, right?
Not ma'am, this question, the quiz 1 question, the proper subspace.
Oh.
Question number 6 itself.
Question, option 2.
Oh.
Yes, this
proper
one.
subspace means. Proper subspace means. Can you please mute if you're not talking to me? Proper subspace means it is a proper subset which is also a vector space. Span of S, you're proving it is equal to R3. Is R3 a proper subset of R3 or improper subset of R3?
Ma'am, how can okay, the all the element is not there, the 1 2 3, only the
when all elements are there, it's called an improper subset. No, the set itself is a subset of itself, right? Every set is a subset of itself. Agreed?
No, ma'am, I am not getting it. Please.
Yes or no?
Hold on.
Set is a subset of itself. Yes or no?
Yes, ma'am. Yes.
Yeah.
Yes, ma'am.
If you take 1, 2, 3, if you want to show something is a subset of something else, you have to make sure every element here belongs to this element, this set, right?
Yes, ma'am.
It belongs, right?
Yes.
So every element is a subset of itself. Every set is a subset of itself. And that is called an improper subset.
Okay.
Proper means it's properly contained inside the set. Here it is. It's not properly contained, right? It's the set itself. Other doubts?
Ma'am, question number 9 in the mock. Can you explain that also?
Find out the correct statements from the following. The set of all invertible matrices forms a subspace with respect to usual addition. So, what is it that you want to explain? Do you know what a subspace is?
Yeah.
You know what are the conditions you have to check, right?
Yeah.
So, did you check all the 3 conditions for this? Does it satisfy all the 3 conditions?
No, the first one, the set of all.
Is it closed under addition?
Ma'am, actually, it's
Okay.
enough to check the first condition. Zero vector doesn't exist here.
Oh, yeah, the 0 vector itself does not belong to this set, right? Yeah.
Okay, okay.
Determinant of the 0 matrix is 0, right? It's not non-zero. So.
It's not invertible, that's why.
Yeah.
Okay.
And what is the second option is still?
Second option, the vector subspace, vector space R5 contains 2 disjoint subspaces. Disjoint means what? They don't have any element in common, right?
Yeah.
But then every subspace has the 0 vector, right?
Yes.
So it can never be disjoint, right? 2 subspaces can never be disjoint.
It's the common element.
Ma'am, even can you please explain this one, ma'am? Union of 2 linearly independent sets need not be linearly independent, and intersection.
What is intersection?
No. The union of 2 linearly independent sets need not be linearly independent.
Okay. Is this a linearly independent set in R2?
Yes.
Yes, ma'am.
How will you check it is linearly independent?
Determinant is not equal to 0.
Determinant.
Is this a linearly independent set in R2?
Yes.
Yes, ma'am.
What is the union of them?
1, 1, 1, 0, 2, 0.
Is this a linearly
No,
independent set?
Because
Okay,
1,
no.
0,
No.
2, 0, these are
It's
scalar
a
multiples.
Okay.
Dependent.
Okay. Dependent. There is linear combination. Okay, ma'am. Understood. Thank you, ma'am.
Okay.
Ma'am, may I leave, ma'am?
Yeah, please. If you have doubts, you ask. Otherwise,
Thank
we'll
you, ma'am.
close.
So tomorrow's session we'll start with spanning, ma'am. Spanning of S. Span of S.
I'll ask him to start from vector space, definition of a vector space, quick recap of that, and then do linear independence, dependence, span, basis. Yeah.
Because I may join at 6:30. That's why I'm asking, ma'am.
This video will be shared, right?
Yeah.
Okay, thank you, ma'am.
Thank you, ma'am.
Thank
Good night.
Thank you, ma'am.
Okay, thank you, ma'am.
Ma'am, when we upload this session on
All the
YouTube.
best for the exam.
Good night, ma'am. Thank you, ma'am.
Thank you, ma'am.
Ma'am, hello.
Yeah.
Ma'am, when will you
Can I
upload
ask
this
one
session from
small
YouTube?
doubt?
I will try to do it by tonight. Means we have to make sure, we have to check if the studio team person who's in charge is awake. That's why.
Could you share PDF?
Yeah, PDF immediately after the session.
Thank you.
Thank you.
Yeah, okay, ma'am.
Actually,
Thank you, ma'am.
Yeah, thank you. Yes.
in
Thank you, ma'am.
in 3.2, question 4, first option.
3.2, question 4. First option. Okay.
AB is equal to 0 for all V belongs to V, then A is equal to 0. But if V is a 0 vector, then in that case A should not be 0, right? Then why it is written that for all V belongs to V, except for 0 vector, that should be written.
AB is equal to 0 for all V in V. For all V in V implies A is equal to 0, right? This is the question, right?
Yes.
Yeah. So, what are you saying?
But if V is a 0 vector,
Okay.
then A
If
need
V
not be
is 0
0.
vector, this is satisfied, right?
Yes.
But A need not be 0, right?
Yes.
But this is not satisfied just for the 0 vector, right? This is satisfied for every vector V.
Then it should be written that except 0 vector.
No,
in
why?
The question.
Why?
Yes, because for all other vector other than 0 vector, we have to write A as 0.
No.
Then only.
No. So, A into, let's take V as real numbers, okay? Means the vector space. Or let's take it as R2. Fine?
Okay.
You are saying we should write, we shouldn't include this, right?
Yes.
So, does 1 comma 1 belong to R2?
Yes.
So, I should get, this is what I am given, right?
Yes.
So, do I get A is equal to 0?
Yes.
Then I can put A is equal to 0 here. I'll get 0 into 0, 0 is equal to 0, 0, right?
But
it is true for it is true for every vector.
Okay.
Is it true here?
Yes.
Because it's true for every vector. This is not going to contradict when I put it for 0, right?
If you put A is equal to 1, then
if I put A is equal to 1, this statement is not true, no?
No, then 1 into 0, 0 is equal to 0, 0.
Yeah, but 1 into 1 comma 1 is not equal to 0, 0, no?
Yes.
It is holding true for every element in R2. So it will hold for A 0, 0 also, for 1, 1 also.
Okay, ma'am. Got it. Actually, I got that second option, but with first option I have confusion. That's why.
Okay.
Okay, ma'am.
Okay.
Ma'am, we say like closed under addition. That means whatever we have defined according to that, it should be closed under that, right?
Yeah. Whatever addition is defined, that. Okay. Any other questions?
No, ma'am.
Okay.
No.
Then we
Thank you, ma'am.
Yeah. Thank you. All the best.
Thank you,
Thank you,
ma'am.
ma'am.
Good night.
Good night.